Hello, Year 10. This is the lesson 1 for the booklet 1.4 Domestic Electricity. So, we'll have a look at some slides in just a moment, but let's see if you can remember the 8 forms of energy Give this a go then. I'll give you a clue. Obviously, I'm speaking to you. Sound is a type of energy. Pause this, write in as many as you can, and then I'll go through the answers afterwards. So let's have a look at the other forms of energy that you should have. Well, these diagrams say it all. I'm thinking with this sprinter here, dye green, we've got some movement there, kinetic. Movement energy, kinetic. These builders are in the USA, Manhattan, I think in the 1920s or 30s. They're very, 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 very high up. So they've got a lot of stored gravitational potential energy. We call that GPE. Think about what would happen to an egg if you released it from the top of that skyscraper. It has a huge amount of stored potential energy. Now, just underneath, we've got hamburger. Hamburger, any foods are actually a type of stored energy. They are, of course, stored chemical energy. And the last one that we've got here is a battery. Now, if you were to link up that battery to a bulb, you would get the flow of electricity. Through this circuit. And conventional current flows from positive to negative. So what do we have here? Electrical energy. So there's the first 4. Let's move on. This ball, this chemical, is emitting not only light, but also heat. Obviously, they are 2 separate forms of energy. This one, with his headphones, a sound. We've already looked at that, haven't we? This chap here is pulled back an elastic band, so there is a lot of stored elastic energy in that elastic band. Same for a bow, an arrow, same for a spring. And this last one here, I don't know whether you know what it is. It's actually a nuclear bomb. Contains a huge amount of stored energy, nuclear energy. So they are our 8 forms of energy. So let's move on. Appliances and machines. These transfer energy from one form to another. For example, a toaster transfers electrical energy into, well, useful heat. And if you've ever looked inside a toaster when it's on, you can see the bars and you can see that they're orange. So we've got a type of wasted energy there, wasted light. Useful and wasted energy. When energy is transferred by an appliance, only part of it is usefully transferred. Some of the energy is wasted. So we've got energy going in and we've got energy going out. So the energy that goes in is electric. Electric in. Now we've got some useful energy out. So we've got useful heat. We've also got useful kinetic. Inside a hairdryer, you've got a fan, and the fan pushes out the air particles and heats them up. This is useful. However, I'm sure you'd recognize that some of the energy out is wasted sound. Now, wasted sound out. We've also got useful heat out and useful kinetic out. Now, I'm going to give you some values now, and I want you to try and work out the other one. So the electric in, I'm just taking numbers out the sky now. I'm going to say that 800 joules of energy goes into the hairdryer every single second. Okay? 800 joules per second. In other words, is 800 watts, because a joule per second is watts. Okay? So, just making these numbers up now. Let's say that the wasted sound out, let's say that that was, making these numbers up, 157 joules per second. The useful heat out, 312 joules per second. Can you work out what the useful kinetic energy was? It's pretty simple. I'll come back in a second and explain. Okay, well, here come the workings. I'm going to add up the 312 and the 157. I'm showing my workings here for the examiner. The energy in is 800. If we take away the 469, we should then work out what the useful kinetic energy was. Using my calculator now. Always can use a calculator in your science exams. But I'm showing the examiner my workings, and the answer is 331 joules per second. So that value here relates to that there. So, done. I've added in the energies in and the energies out. What you should understand, and this is the absolute basics now, absolute basics. Is this the energy that went in equals all of the energies out. It's as simple as that. The energy that went in equals the energy that went out. Energy can't be created, it can't be transferred, it can't be destroyed. Energy can't be created, it can't be destroyed, but it can change from one form of energy into others. So, what did you notice about the energy in and the energy out? It's a very simple equation. The energy in equals the energy out. We have here a table to complete. It says use 2 appliances from the top row and only 1 from the bottom. Okay. I am going to pick the kettle and I'm going to pick the washing machine as well. You pick another one from the top. So the washing machine, I'll have a go at that. Washing machine. The energy that goes in, it's electric. In fact, all the washing machine, the TV, the kettle and the light bulb will all be electric. Of course, the motorbike works off petrol, and so that will be the energy in is chemical. Now, the useful energy out from the washing machine, we've got kinetic, it spins. It also releases heat to help dry the clothes. Wasted energy, you've got a lot of sound there, haven't you? And the kettle, spelt correctly. The kettle, that's electric. And the useful energy out, that's heat. Wasted, it's got to be sound. It will actually waste some heat energy as well, and it will be sent to the surroundings, be lost to the surroundings. So complete this table. I didn't complete it all, but you complete this table if you would. And let's just have a look here. This table lists common appliances and a typical power rating or a range, because they can vary. So let's just have a look now. Fridge. A fridge. Let's say it's up at the higher end, so it's 120 watts. Remember, what does that mean? Well, it transfers 120 joules of electrical energy into heat every single second. Whereas, if we have a look at a desktop computer and we'll look at the lower end, it is only 80 watts. So it transfers 80 joules of electrical energy per second, and it transfers it into, so it converts 80 joules of electrical energy per second into probably useful light, useful sound and wasted heat. Now, I think the final points to consider during this lesson. As more transfers take place, the energy becomes more difficult to use for further energy transformations. So let's take, for example, a kettle. If you transfer electrical energy into heat, how are you then going to use that hot water to power something else? It would be quite difficult. Not impossible, but difficult to then convert their heat energy in that water into other forms of energy. It's just difficult, right? And final consideration is both wasted energy and the energy which is usefully transformed are eventually transferred to their surroundings, which become warmer. Okay? So, for example, a kettle again, you're converting electrical energy into heat energy in the water, but that heat energy in the water is then lost to the surroundings, so the surroundings eventually heat up. Okay, that's the end of lesson 1.